Hey guys, today we're going to be talking about Newton's three laws of motion. So these are super important in physics. So Newton's first law of motion. So basically says an object in motion tends to stay in motion, object at rest tends to stay at rest. So you have heard of this before, right? So what does this mean? It means that a moving body will continue moving at the same speed with this in the same direction until a net force acts on it. Now, Newton is actually a lot smarter than people think because he was able to realize this even though in our everyday life objects do not act like this, right? If you throw a ball, will it keep going on forever? Of course not, right? It falls, quickly to the ground, it slows down, it's doing all kinds of things. Well, why is that? Because forces are acting on it all the time. So friction and gravity, these forces are acting on objects all the time. Also, an object at rest will remain at rest unless a net force acts on it. This is more true to what we experience every day, right? If you leave an object on a table, it's not going to move unless something moves it. So no surprises there. What you should know, though, is in space, if you were to take that same baseball and throw it, it would travel in the same direction and the same speed for hundreds, if not thousands, or maybe even millions of years until a force acts on it, which could be a long, long time. All right, so there's this concept of inertia. When people talk about Newton's first law of motion, they will often use this word. They may use the word inertial forces. There is actually no such thing, but it looks like there's a force acting on an object. So let's look at some examples. So the first example, we have an astronaut. He is in space, not attached to the space station, right? He will continue drifting in the same direction and at the same speed, probably almost forever. Now think about it. If you were doing a spacewalk outside of the International Space Station, and these guys are usually attached by a chain or a rope of some kind. But if they would become not attached and started to float away, how could they get back? Well, they actually have canisters of a compressed air built in to these suits, much like the air that you might use to clean off a keyboard to get the dust out of it. And so they can simply press a button and sort of jet these so that they can head back to the space station if for some reason they get separated. But this is not something that you want to have happen to you, right? You don't want to become disconnected and be kind of floating away indefinitely forever away from the space station. Not a good situation. Another example of this Newton's first law, or the inertial forces, as people often say, is that if you're in a car and you're going 65 miles an hour, the speed limit hopefully, and you have an accident, your car comes to a stop very, very quickly, right? In a very short period of time. But remember, your body is still moving at 65 miles per hour. So something has to stop you. So that could be the seatbelt, hopefully, or maybe the airbag. Or if not, then the windshield will be the one that stops you. So obviously you want the seatbelt and the airbag to be the things that stop you and not the windshield itself, because you'll get really seriously hurt. You've experienced these inertial forces when you're in an airplane and the airplane is taking off and it pushes you back in your seat, or when you're landing, right? You're gonna and the pilot hits the brakes and you're gonna kind of surge forward, right? So again, your body wants to keep going forward or stay, or to keep going backwards or to stay where it is unless a force acts on it. Hopefully it's a seatbelt. So we do talk about net forces for a bit, because you can have multiple forces acting on an object. So here we have an object. We have three forces that are acting on that object. So the vectors here show you the direction of those forces and also show you the magnitude. So obviously this is a shorter arrow, this is a longer arrow. So the magnitude, or the amount of this force, is significantly larger than this force. When you add them together, this is the net force. This is the direction and magnitude of the net force. Now, we're not going to get into it too much because there's quite a bit of complicated math when you have a bunch of forces going in a bunch of different ways. We're just going to be looking at two forces going at right angles to one another. These are not exactly, but that's the only kind of situation we're going to look at. But if you have more than one force that's acting on a body, this is the net force, right? And of course, we add these together. So you've heard this word net before, right? It's just sort of once you add and subtract everything, what are you left with, right? What is your net pay? When you get your paycheck, once you pay taxes, and this and that and the other thing, what is your actual net pay that's in your paycheck? So here we have an example. We have two teams here. Each team is exerting a force of 500 newtons. This one going this direction, this one going in this direction. So what is the net force? Well, you probably guessed it. The net force is 0, right? Because these are going in the opposite ways. And so what's the acceleration? Well, the acceleration should also be 0, right? These guys will be, deadlocked and nobody will win. Nobody will move anywhere. There will be no acceleration. So when the net force is 0, we often call this equilibrium. So if you hear that term, don't be thrown off by it. What if we have a situation, though, where we have two teams? One team is exerting 400 newtons of force this way. The other team is exerting 500 newtons of force this way. Well, you guessed it. This team is going to win, right? They're eventually going to pull these guys this way. So what is the net force going to be? Well, because he was going opposite ways, we have to subtract them. So it's actually going to be 100 newtons of force going this way. All right, so there will be some type of acceleration. And that is because the net force is not 0. In this case, it's 100 newtons. Let's talk about mass and inertia right now. So if you kick a soccer ball with the same force that you kick a bowling ball, what's going to happen? Which one is going to accelerate more? Well, first of all, if you kick a bowling ball, your foot's going to hurt. But if you kick a soccer ball with the same force, obviously the soccer ball will accelerate more. And why is that? Well, the soccer ball has less mass or weighs less. We're going to make a distinction between mass and weight a little bit later, but it has less mass than the bowling ball. So therefore, it takes more force to make the bowling ball accelerate the same as the soccer ball. And this makes sense. If you're pushing a heavy object, it's going to simply take more force for you to push that heavier object at the same speed as the lighter one. Now, but once the bowling ball gets going and the soccer ball gets going, which is going to be harder to stop? Well, as you know from experience, right, again, mass or weight is going to play a factor here, right? So the bowling ball has more mass, so therefore it's going to be harder to stop than the soccer ball. So let's say someone kicked you the bowling ball and you wanted to stop it so you could kick it, you're going to have to apply a very high force to stop that so you can then turn around and kick it into the goal. So this idea of inertia is that it's things with a lot of mass are harder to get moving. You have to apply a greater force, but they're also harder to get to slow down. So think of something that's an object that's really big, like a car. It takes a lot of force to slow that down, right? You couldn't just stand in front of a car going at 55 miles an hour and just gently push it in the opposite direction to stop it. That simply would not work. So the greater the mass, the greater the inertia, and therefore the greater the force that's required to accelerate that object. Okay, so let's talk about balanced and unbalanced forces. We've already kind of alluded to it a bit, but balanced forces occur when the forces are equal in magnitude, so they're the same amount, but they're going the opposite way. All right, and if this is the case, if you have balanced forces, how do you know you have balanced forces? Well, the object is not accelerating, and the net force is 0. Now, we do have to be careful here on Earth when there are balanced forces. Typically, the object is not moving. However, in space, you could have balanced forces and the object is moving but not accelerating, right? So in other words, It's going in the same, direction and the same speed. So balanced forces. Unbalanced forces is just the opposite. This is when the forces are not equal. So in the case of the space shuttle, taking off, gravity's pulling down, but obviously the rockets associated with it are producing thrust. Those are pushing up against gravity, and these forces are not equal. The force of the thrust is greater, so therefore it accelerates, right? It starts to leave the Earth. And so in the case of unbalanced forces, we know the forces are unbalanced because they have a net force, and we know because the object is accelerating. Newton's second law, we've already kind of tackled it a bit, right? It's just the formula. The net force is equal to the mass times the acceleration. You guys have already done problems associated with this. I just want to mention really quickly that this goes back to what we talked about, that this law is saying that, again, the higher the mass, the more force that's required to move it, right? Or the more you accelerate it, the more force that's required. If we have forces that are going the opposite way, we can subtract those forces. If the forces are going the same direction, we can add those forces. So in this case, these are going the same way, so we can add this, and we can get 42 newtons of force going to the right. But of course, we have some force going here, so it's going to be 42 minus 15. So it will be 27 newtons to the right. So if you ever come across a situation where you have forces going the opposite way, you can subtract them and figure out what's going on. All right, lastly, Newton's third law of motion. You've probably heard of this one too. For every action, there is an equal but opposite reaction. All right, so if you hit a tennis ball with a tennis racket, the racket's hitting the ball and exerting a force on it, but the ball is also hitting the racket and exerting a force on the racket, right? If you were to fire a rifle, the bullet obviously is going to go forward, but what's going to happen? You're going to have, kickback, and the rifle is going to move backwards. This is why you normally hold the rifle against your shoulder to prevent the rifle from flying backwards. So we've already kind of alluded to this and talked about this a bit when we talked about cannons and that sort of thing. But it's the same basic concept. So a few more examples that have to do with Newton's third law of motion. And that is a balloon. If you have a balloon, of course, if you blow it up and then you let it go, the balloon goes forward. So why is that? Well, I think most people can easily see the reason for that is that the balloon goes forward because the air is coming out the backside of the balloon. Equal but opposite reaction. Now let's take a look at a rocket. If we look at a rocket, if I ask students, why is the rocket going up? They say, well, it's pushing off the launch pad. And if I say, well, if the rocket is, a mile up in the air, they say, well, it's pushing off the air. And then if I say, well, if it's in space, what is it pushing off of? And they say, I don't know, right? And so there's nothing in space, right? There's no air, there's no launch pad. So obviously it's not pushing off any of those things. So the rocket actually works very much like the balloon here, right? Except, obviously, instead of air coming out the back, it's actually hot gases that are, exiting the back of the rocket. And those hot gases are exiting very, very quickly, right? So you're mixing oxygen and fuel inside the rocket. You're igniting them somehow, and those hot gases are, coming out the back of the rocket. And that is what is going to propel the rocket forward. So again, a rocket is very much like a balloon in the sense that it is a great example of Newton's third law of motion. And this is a good thing because when you're in space, you can simply turn on the rocket, and again, same thing. The gases will go out the back, and the rocket will go forward, even though there's no air or no launch pad or anything like that. All right, so I hope this was helpful. Make sure that you answer the questions associated with this little lecture, and that'll do it for this week.